All right, guys. Today we're going to just do the second part to this set of notes on the layers of the atmosphere. I know you did a little bit with this yesterday. I just want to talk about some more details about some things, and then you're going to do a few questions about everything. So let's start with just this. You guys know this is page 14 of your reference table. We talked about this in the previous video, part one. And again, the layers of the atmosphere working your way from the surface up: troposphere, stratosphere, mesosphere, and thermosphere. The thermosphere actually can be broken into two parts: the thermosphere at the bottom and the exosphere at the top. They don't have that on the reference table. It's not something you really need to know, but I just wanted to mention that in case you ever see that in the future. One thing that's kind of important about this, obviously, we talked about the fact that the layers are different from each other based upon the way the temperature varies over elevation, or over altitude, I should say. Um, but something that's also interesting is the idea of pressure. So we're going to talk about pressure as a totally separate study later on. We'll talk more detail about this, but air pressure decreases quite dramatically as you rise up in altitude through the troposphere, and then it pretty much stays the same at a pretty low pressure once you get up into like the middle of the stratosphere or so. Okay, so from ground level all the way up to the top of the troposphere, called the tropopause, it drops quite a bit. And the reason it drops quite a bit is because we lose a lot of the mass of those air molecules. Most of the air molecules in our atmosphere are at the bottom because they are pulled down by gravity. So most of the molecules are kind of hanging out down here. They're getting squished together down here, and therefore there's more pressure, more weight from all those the air molecules, therefore more pressure. Okay, and you can kind of see that in this diagram here. Lots of air molecules at the bottom, all kind of getting squished together, and as you rise up in altitude, they are a little bit further apart. They're spread out more. There's less pressure. There's less weight. Okay, so think about air pressure in terms of the amount of molecules that are present. Okay, and if they're far spread apart like that, they don't give off as much pressure. Okay, and that's kind of an important a concept for this whole meteorology unit. Okay, so this shows the exact same thing, noticing how the air pressure changes over altitude. At the surface, we're somewhere in the 1,000 millibar neighborhood, or 1 atmosphere. And then as you climb in the atmosphere, it drops pretty dramatically. Mount Everest is actually not drawn correctly on this diagram. It should be right at this 5.5 dotted line at the top of it, but it is a very low pressure at the top of Mount Everest. Okay. Once you get up into this region up here, 40 kilometers up, it pretty much stays the same pressure the whole time. All right. Now, just to break down the troposphere a little bit more, troposphere is most important. Why? Because, well, number one, we live here, but also because there's water in the troposphere. And that's very prevalent, which makes all of our clouds, which you guys learned about the other day. Another interesting thing about the troposphere is the way that it heats up. So remember, we have all this incoming solar radiation, also known as insolation, that warms up the atmosphere. Right? It collides with the molecules of air. They start to speed up. They generate energy, and they move around, and that's essentially what we call heat. Okay. Now the surface is getting heated up more. The land surfaces, the water surfaces, they're getting heated up. They give off their own radiation and warm up the atmosphere down here. So the surface of the Earth, the lowest parts of the troposphere, are getting the most energy. They're the hottest. And so as this warm air rises because it's less dense, it gets up into the top of the troposphere and it cools off quite quickly. Why does it cool off? Because there's less pressure. As air expands outward, that pressure drop is going to cause a temperature drop. And that's what causes clouds to form. So this cumulonimbus cloud that you see here, you'll notice the bottom of it is very flat, and that is due to the fact that the pressure is dropping, and you get up to a certain pressure and a certain temperature, and we reach what's called the dew point, and that's where the clouds start to form. And so most of the cloud bottoms are pretty flat. Okay, and this cumulonimbus cloud climbs all the way to the top of the troposphere and kind of spreads out there because the pressure is really low up there. And that's an important idea, is that we have mixture of gases and mixture of temperatures in the troposphere. That's what causes weather. That's what causes the wind outside right now. It's a super windy day here on Thursday, the 30th of April. Okay, why? Because we have differences in temperature, we have differences in pressure, and that's what causes the air to move. So the troposphere is in constant motion. Okay, and you guys might recall this demonstration here that we did early in the year, where we had the hot water and the cold water, and we put them on top of each other. And we saw that when the hot water is on top and the cold water is on the bottom, there's absolutely no mixing because everything's stable. Everybody's happy here. The warm is up top, the cold's on the bottom, less dense, and nothing really wants to move. Now, over time, yes, these will eventually mix. They'll get to the same temperature and they'll mix. When we put the cold on top and the warm on the bottom, we noticed that the warm water wants to rise and the cold water wants to sink. And so you have an immediate mixing and they mix colors and it kind of makes a purplish color, as you can see there. This video shows that as well. So if you want to check these notes out later, I also did this with my kids and I might insert that little video clip right here. The red bottle is hot water and the yellow bottle is
cold water.
And we have them flipped on top of each other. Any predictions on what's going to happen?
The white is going to go into the yellow.
You think they're going to mix?
Yeah.
Or what do you think, Micah?
I think they're going to mix too.
What about you? You don't think they're going to mix? Okay.
No.
All right, so Micah, you're going to pull the little plastic out, okay? Slowly. Towards you. Go ahead, keep pulling.
It's hot.
Keep going.
Hot.
Keep going. Okay.
It mixed.
Alright, so we'll leave it like that. And as you can kind of tell, there was a little bit of a spill there because we didn't have quite enough water in there, but look at the bottom and look at the top. Did they mix?
Yeah. Yeah.
Did they mix completely?
No.
Watch your head's in the way so they can't see on the video. Okay, so we're gonna take a look at that. Yellow is on the bottom for the most part, and the red is on the top for the most part. A little bit of mixing in between here. Okay, but why does the red water stay on top?
Because it's hotter than the colder water.
Yeah, and therefore it's less dense. It stays up top. Okay, good. Okay. This is a cumulonimbus cloud that was, I took this picture from my front window of my house across the street. This is kind of looking towards Syracuse. It was a pretty strong thunderstorm that had passed through. And I was taking this around sunset. The sun was shining off the cumulonimbus. You can see it spreading out up here at the top of the tropopause. So we're talking about 10 kilometers high, okay, 7.5 or 8 miles or so. That's how high up those clouds get. And there's a lot of mixing going on here. The warm air is rising and cooling off and then sinking back down again. And all this mixing is causing this storm. So just remember that the troposphere is where the weather takes place. It's the most important layer as far as weather is concerned. And this is the one that's going to concern us the most. And remember, this is where the water is located. Okay? All right, so that's the troposphere. Now, this diagram is actually also in your reference table. We looked at this when we talked about the Coriolis effect. We were talking about the curve of winds across the surface, which causes the ocean currents to curve across the surface. And we'll talk more about this more in detail, but I want you to notice this dotted line here is labeled the tropopause. So these arrows are showing the convection that's happening in the troposphere, okay, the air movement in the troposphere from about 0 up to about 10 kilometers. Obviously, this is not to scale, but you can see this mixture. What causes this movement? It's differences in temperature, which are caused by differences in pressure, which are caused by uneven heating, the spin of the Earth, a whole lot of factors, which we're going to get into later on. Okay? All right. Stratosphere, the next layer up. The important thing about the stratosphere is the idea that we have a complete switch and turnaround from our temperature decreasing. Now we're going to have temperature increasing with altitude. And the reason that's true is because of this molecule called ozone. Ozone is an interesting molecule because it's made from oxygen. Ozone is just O3. Oxygen comes in a molecule called O2. So when UV radiation, remember solar radiation, we have all of that stuff coming down through the atmosphere. UV radiation, which is in a certain wavelength, will hit oxygen molecules in the stratosphere, and it will split them apart until you have two separate oxygen molecules. So going from O2 to two oxygens separate. Now those two free oxygens are going to want to pair up. They're not stable by themselves. So they like to pair up with things, and they'll pair up with other oxygen molecules, and they will make what's called O3, which is ozone. Now, ozone, in the process of doing this, in the process of splitting the oxygens apart and forming ozone, we are releasing a lot of heat, a lot of energy is produced. And that's what warms up the stratosphere. That's why we have a switch. It's not getting colder as you go up, it's actually getting hotter. Oxygen, O3 ozone molecules can also be split apart by UV radiation, and then you can recreate the oxygen in the separate oxygen molecules. So that's kind of cool. You have like a constant recycling process happening. So you have energy releasing all the time. Now, the great thing about the ozone layer is the idea that it is absorbing UV and preventing all that harmful UV radiation from coming down to the surface, which will or can cause some pretty harmful stuff like cancer, skin cancer. Now, the air in the stratosphere is pretty dry. There's not a lot of water up there. It's a little bit further apart. The oxygen molecules and the nitrogen molecules that are there are spread apart more. So we call that a thinner atmosphere. And therefore, there's not as much turbulence. There's not as much mixing. In fact, it's very, very stable, which is why airplanes like to fly around up there because it's very stable air. It's very nice for cruising, and you don't have to run into all the nastiness of clouds and mixing of air. Okay, so airplanes fly right in the stratosphere at the bottom of the stratosphere. This video here talks a little bit about the ozone layer, the hole in the ozone layer, which was caused by chlorofluorocarbons, which were produced especially back in the 60s and all the way up to the 80s. They stopped producing CFCs, and our ozone is actually healing itself, which is helpful because obviously ozone protects us from harmful UV. Okay? All right, mesosphere. Meso, the prefix means middle, which is kind of misleading because the mesosphere is like one of four layers. So it is in the middle. The stratosphere and the mesosphere are in the middle. Now, interesting thing about the mesosphere is we have a complete reversal again. Now we have the temperature decreasing with altitude. We have less absorption of solar radiation. There's no ozone here. And we actually have a little bit more cooling from carbon dioxide. All right, so there's a little bit more spread out here. The molecules are a lot more spread out here. Now, they're spread out, but they are all mixed together. Remember, the stratosphere was like not mixing. It was pretty stable. The mesosphere, there's a lot of mixing going on in this layer. And therefore, it's kind of this mixture of gases that causes a lot of friction. And so when we have meteorites that come into our atmosphere, they come in and we call that a meteor shower or a shooting star. As they come into the atmosphere, they come in contact with this thick mixture of gases in this region, and they essentially burn up because of all that friction. Now, there is an estimate here of about 48.5 tons of meteoritic material that falls to Earth every day, which is kind of crazy. If that all came down, that wouldn't be good. So we're happy that we have the mesosphere to burn up most of that stuff. Now, when the astronauts come in from outer space back down, they have to pass through the mesosphere. And in the process of doing so, they have to come in at a good angle. They have heat shields as well that protect them from burning up in the mesosphere, which would be obviously terrible. So they have this heat shield that protects them on the front of their space shuttle. Okay, so that's the mesosphere. Interesting thing about the mesosphere, it's the least known layer of all of them. It's hard to stick around in this layer. The only data we really have are from rockets going through it, and they only spend a couple of minutes in there. Interesting graphic here. Again, meteorites are burning up in the mesosphere. You'll see different color meteorites, and that's due to the content, the chemical composition of them. As they burn up, they give off a different wavelength of energy, which is something you'll learn about in chemistry class next year. but they give off these different colors based upon what they're made out of, which is kind of cool. All right, thermosphere, the last layer that you'll need to know about. The thermos prefix, thermo, meaning heat, right? And in this case, now we're not getting colder with altitude, we're getting warmer, and quite warm. We're talking 500 to, I've heard, 2,000 degrees Fahrenheit in this layer. So it's really, really, really hot. And what's going on is that we have a lot of solar radiation that's exciting the gas molecules in the top of this. There's not very many of them. They're really far spread apart. And in the process of getting hit by solar radiation, they get super excited, they speed up, they ionize, which means they lose electrons. And so sometimes it's called the ionosphere for that reason as well. Okay. Now, interesting fact here, it wouldn't feel hot, and that's kind of a weird idea because you wouldn't be able to live up there or hang out up there because there's no oxygen really, and so and then not nearly enough of it. But you wouldn't feel hot because there's not very many air molecules around. Heat is really due to the fact that there's a lot of air molecules that are colliding with your skin. Okay, and you feel it. But they're so far spread apart, you wouldn't really know that. We measure the temperature based upon the speed of the molecules, and they're going super fast, and that's why they're up to 2,000 degrees Fahrenheit. In the thermosphere, around 250 miles or so up, the International Space Station orbits around that region. This is really considered to be the beginnings of outer space, and then it kind of phases out or kind of disperses out as you go up into higher altitudes above the Earth's surface. Okay, so this is really the beginning of outer space. In the picture on the right, you see the aurora. The aurora borealis is in the north, and the aurora australis is in the south, the North Pole and the South Pole. This is due to the magnetic field and the ionized molecules that are in the atmosphere, which I'm going to show you guys a video about a little bit later on. And this is that video that I'm going to play a clip of. And it's a really good video and talks about the mesosphere and the thermosphere in good detail.
The mesosphere starts at 50 kilometers and ends at roughly 100 kilometers. Towards the top of this layer can be found the coldest places on Earth, where the temperature can drop as low as minus 143 degrees centigrade. Again, there can be a very rare type of cloud found in the mesosphere. These are called noctilucent clouds, and they are again very beautiful. Found between 50 degrees and 70 degrees north and south of the equator, and around 76 to 85 kilometers up, they are the highest type of cloud found on Earth. Like the stratosphere's nacreous clouds, they can only be seen while the sun is below the horizon. They are a type of water ice cloud, the difference being they can form with or without collecting on dust particles and are sometimes purely water vapor clouds. The source of the water and dust this high in the atmosphere are not known with certainty, but could come from micrometeors or volcanic eruptions. Water vapor from rockets can also cause noctilucent clouds, most recently from the SpaceX rocket Falcon 9. They are really spectacular, especially when you consider how high they are. This is a view from the perspective of the International Space Station. Even in this image, you can visibly see the different atmospheric layers, the troposphere, stratosphere, and mesosphere. Interestingly, the mesosphere is the least understood of all the atmospheric layers, even referred to as the ignorosphere, as it's above the flight capabilities of aircraft and below the minimum safe orbit of satellites due to atmospheric drag. The only times measurements can be taken are by rockets, and only for a few minutes as they ascend to the thermosphere, the next atmospheric level. As you might have guessed by now, above the mesosphere at roughly 100 kilometers is the mesopause. And as you might have guessed again, the mesopause is the point where the temperature stops decreasing and starts increasing again throughout the thermosphere. In fact, temperature can get extremely hot in the thermosphere depending on the solar activity, as much as 2,000 degrees. Although it's so hot here, because of the exceptionally low air pressure at this point, there are not enough gas particles to transfer much heat, so it would still feel well below 0 degrees. To give you an idea of how little gas there is here, above 160 kilometers, Molecular interactions are so low that sound cannot travel anymore. The thermosphere is the thickest of all the atmospheric layers, rising from 100 kilometers all the way to 600 kilometers, but it only contains 0.002% of Earth's atmospheric mass. The thermosphere is actually considered by a lot of people to be the start of space. Satellites, and even the International Space Station, orbit within the thermosphere. But that's also why many satellites' orbits degrade, eventually with them burning up in the lower parts of Earth's atmosphere, because they were never really in true space, and atmospheric drag was still slowing them down enough that they eventually fell out of orbit. The thermosphere also serves an important purpose to us on Earth. A lot of the most dangerous and highest energy electromagnetic waves from the Sun are absorbed in the thermosphere, and the effects of this can be seen as beautiful aurora in the sky. These high energy waves interact with particles high in the thermosphere, exciting them and making them glow in many different colors, the most common on Earth being green. Above the thermosphere is the thermopause, which can range in height from 500 kilometers to 1000 kilometers, depending on the time of day, the amount of solar activity, and a host of other factors. Above the thermopause is the last atmospheric layer, the exosphere. In the exosphere, there are very light gas particles like hydrogen present. However, due to the distance between these particles, they don't act as a gas, as they do not collide with other gas particles. They are, however, still gravitationally bound to the Earth. Near the thermopause is where this gas stops behaving as a gas due to lack of collisions, and at the top of the exosphere, reaching from 10,000 kilometers to halfway to the moon, is where the sun's radiation pressure on these gas particles overcomes the gravity of the Earth. We are now in true interplanetary space. And there we have it, Earth's atmosphere unraveled. I hope you've gained some insight and learned something today that you may have never known before.